Hello and welcome to this lecture of elements of mechanical vibration. The previous lecture saw us exposed to the basic equations relating to the response of a vibratory system, simple vibratory system to harmonic excitation. We continue that discussion in this lecture. In particular, focus our attention on the phase between the excitation force and the corresponding vibratory response, and then onwards we will get introduced to an important parameter called as the quality factor, which defines the quality of resonance expected for a simple single degree of freedom vibratory system. Okay. Now, with that let's get back to what we were discussing about the phase between the excitation and response, and the expression phi that we derived, which has this expression tan inverse of sorry, it was 2 zeta, right. Two zeta r minus r square. Something which is pretty straightforward here. Okay. So, this phase angle has been shown to be given by tan inverse of the ratio 2 zeta r and 1 minus r square. Now, for the operation where r is less than 1, so this particular angle turns out that it is less than 90 degrees, and so if we have an excitation force in the form of less than unbalance, if I denote this as F, and it is going to spin with the rotation of the shaft, like the force is going to change its orientation continuously, and that is going to excite this kind of a vibratory system, which if you show in the form of a mass spring and a dashpot subjected to a harmonic excitation force given by F naught, let us say cosine omega t. So, at t is equal to 0, the force has a maximum value of F naught, and then as it rotates, the force in the vertical direction keeps on changing harmonically given by this expression. Now, if I plot the response which was given by capital X F naught e to the power j omega t minus phi over square root of 1 minus r square whole square plus 2 zeta r whole square. With this expression, the x will be having a value which is given by this, and it will have a phase which is given by phi. Now, what is the physical meaning of this phase angle is what is shown here. So, if you plot or show this force as a vector here rotating with a frequency of omega, that is what will happen if f is represented as f e to the power j omega t, because if you remember, we have started with the assumption that the force is constant amplitude f naught and varying with the frequency or fluctuating with frequency omega. So, in a phasor diagram here, this can be shown like a vector rotating with the speed of omega. So, at any instant of time t greater than 0, maybe at certain period of time or instant of time t, this is a snapshot of the two vectors, one the force vector and the other one is the response vector. So, instead of x, if I write this as x of t, then this is going to be given by this. So, this is not the amplitude because we have included the time variation here in the form of e to the power j omega t. So, x of t is the response vector shown by this green colored vector. Now, obviously, for a linear system we discussed and very clearly stated that if force is varying with the frequency of omega, the response x is also going to vary with the same frequency. but they would be having a phase difference which is actually given by phi. So, as you can see in this snapshot, the force vector and response vector, they are separated by an angle phi. Okay, that is the phase with which the response shown by this vector lags the force vector, and as they rotate, both of them will rotate at the same rotational speed or angular speed, because both of them have the same frequency of repetition. Okay. And so, if I can show this part to you, that the projection of the tips of these vectors on the time versus amplitude graph is shown here. So, the red one, which is the force vector, is shown by this particular curve, which is f of t, and this green colored vector the curve is x of t. So, you can see that as the force starts with the vertical orientation, it has a maximum value, let us say, and as it rotates, it reduces to 0 after a quarter of rotation of this vector, and then goes to the negative side, and then it continues in terms of time. So, when it is having its maximum peak value here, the displacement vector is still lagging, and that lag is basically your phi, and at that instant of time, if I take the projection, you can see that its value is somewhere here, okay, at time t is equal to 0. And so, obviously, as this force vector goes on in the leftward counterclockwise sense, this particular vector will reach its peak after phi degree of rotation. So, this basically is representing the situation where the response becomes highest at this particular point. By that time, the force would have gone here, and its value will be somewhere here. Okay. So, this is how the relationship between the force vector and response vector is shown here. The response lags the force vector by an angle of phi. So, I will give you another example, that maybe after 3/4 of a rotation, the force vector comes back to this particular horizontal position, which means that the value of this force is 0 here, and at the same instant of time the response lags behind, and it lags the force vector by an angle of phi. Okay. So, after certain interval of time, as this force continues to move up like this, and then the response vector will align with this, it will have 0 value later. So, this force, this response currently having a negative value will have 0 value later at this particular instant of time, and this distance, which is in terms of time converted into angle, is going to be phi. Okay. What is also important, as we have been discussing, that the frequencies are identical. So, this distance in time is going to be 2 pi over the frequency omega. Okay. And if I find out this peak to peak distance in time and convert it into degrees, that will also be related to the same angle. Okay. So, 2 pi by omega is basically the same time period of repetition as the period of repetition for the force vector. Okay. So, this basically highlights and gives you an idea as to what the phase between the force and the response looks like. The force follows the harmonic variation, the displacement or the response, vibratory response also follows the harmonic variation. The only thing is that the peak at the position in time at which they reach their peak values differ, and the response would reach to its peak little later as compared to the force. So, it continues like this is the position at which the peak in the force occurs, the response will occur little later, okay, in time, and that gets converted into the phase phi. Okay. Now, this animation also shows you how the force vector and response vector are moving and how that translates into time versus amplitude graph. You can see that now you can see, let me rerun this. You can see that the force reaches its peak and then the amplitude reaches its peak. In this case also they reached their peak values at different instant of time. Displacement is always following the force. Okay. That is how it tries to catch up with the force. The force leads the response vector by an angle phi, and that phi is something which we have derived the expression for, which was given by this. Okay. That is the meaning of the phase, and that has in a sense may not have much of a value, because all the time we are concerned about the amplitude of vibration. So, maybe we will be interested in knowing what is the peak to peak or a response amplitude, whether it lags by 20 degrees or 40 degrees may not be so relevant, okay, in general, but it has its own role, particularly in some applications, like when you are trying to balance a rotor or a balancing processes, those phase values would be of significance. And there is I mean, it helps in understanding the vibration phenomena better, as we shall discuss in the basic citation case. Okay. Now, the equation of motion that we have all the time talked about, mx double dot plus cx dot plus kx equal to f of t, we shall have a vectorial representation of this equation. Please make a note that this equation is a force equilibrium equation. So, all of these terms that you see in this governing equation of motion are nothing but forces. This is an external force, externally applied excitation force to the vibratory system. This is restoring force acting on the mass. This is the dissipating force acting on the mass because of the presence of the dashpot or a damper, and this is the the inertia force, the fictitious force that we know. We have used this for deriving the governing equation by using the Newton's second law. So, essentially these elements of this equation are all forces, and the governing equation is essentially an equilibrium between all these forces. So, let us look at how these forces interplay with each other, how are they related to each other. So, we start with representing this force f of t at any instant of time, where because after a period of time t, the angle turned by this is, supposing that the force starts with this initial position, after period of time t, the angle made by this force vector is omega t, and the expression that we have started with representing the force, external force, is f e over j omega t. We know that the response is given by this expression, considering the phase lag between the force and the response. This is what we have derived earlier. The steady state component of the forced vibration response is given by capital X e to the power j omega t minus phi. Now, what is the, because there are other derivatives, time derivatives of the response x involved here. So, x dot and x double dot, I know that if I take the derivative of the response and write the velocity term, what would it be? It is going to be j omega x e over j omega t minus phi. Now, you all know from the Euler's identity, this j can be written as what? Right? It is going to be cos pi by 2 plus j sin pi by 2, right. Sin pi by 2 is 1. So, it is going to be j into 1, that is going to be j, right. So, j here can be replaced with e to the power j pi by 2, which means if I use this, I can simply write the velocity amplitude equal to this, and j gets absorbed in the exponential term here, omega t minus phi plus pi by 2. And similarly, from this if I get the acceleration term x double dot, I can write this as minus omega square x e to the power j omega t minus phi. Now, you can also show that minus 1 is nothing but e to the power j pi. Cos pi is minus 1 plus j sin pi is 0. So, you have minus 1 equal to e over e to the power j pi. So, that means I can take the amplitude of the acceleration to be this, and I can write omega t minus phi plus pi. Okay. So, that is what I have got here. The two derivatives x dot and x double dot are having their amplitudes given by these, and their phases are these. So, now if I have to show these forces Cx dot and Kx. So, I can represent the restoring force Kx in the same alignment as the response itself, because the restoring force is proportional to the response amplitude. Okay. So, at any instant of time Kxt is going to be shown the way I am showing it right now. So, what I am going to do is I am going to focus on this governing equation of motion. I am going to write and show these forces. So, the first of these forces, the externally applied force F e to the power j omega t is already represented here, as you can notice, and that is equal to what? The restoring force Kx is now going to be what? If you replace x of t here into this expression, it is going to be k into capital X e to the power j omega t minus phi. This is what the restoring force would look like, but this restoring force has an orientation omega t minus phi, which means that its angle made with respect to time t is equal to 0, which it started from here. The force F is already having the orientation omega t, which is given here. That omega t minus phi, this is the phase between the force and the response. So, this response will align like this, which is of course aligned with the response. Okay. So, Kx amplitude of the restoring force with proper orientation or the angle made is going to get aligned like this. So, this is going to be the restoring force Kx. What about the damping force? Now, the second one is this damping force, which is going to be what? X Cx omega e to the power j omega t minus phi plus pi by 2. Plus pi by 2 is, this is an additional phase we have to add to the phase of the response, which means that the vector will get oriented 90 degrees ahead or 90 degrees to the response x, and therefore, the dissipating force will get aligned like this. Actually, these can go opposite to the displacement, right, strictly speaking, but then we are all drawing a force polygon. So, even if you draw them along x, it will finally turn out to be the same force polygon. So, this C omega x is the dissipating force leading by plus pi by 2, and therefore, this angle is plus pi by 2 with respect to the angle made by the restoring force Kx e to the power j omega t minus phi. And then what? The last one is this mx double dot, which is going to be m omega square x, that is going to be its magnitude, and it being leading by 180 degrees to the restoring force. So, it is going to be just 180 degrees ahead from the response. Okay. So, that is basically is going to be the orientation of sort of an inertia force here. So, you can notice that this governing equation is nothing but forces in dynamic equilibrium, and all of them make a perfect force polygon with f of t closing all the 3 vectors, and their orientation or their phases are like restoring force, the dissipating force leads the restoring force by 90 degrees, the inertia force leads the dissipating force by another 90 degrees, and this is how they close. Okay. So, this is the representation of the same governing equation of motion in a vectorial form. Okay. Now, here what is assumed is that your phi is in this particular case assumed acute, right. Can you see that the angle was maybe 40 degrees or so, and that is how this polygon gets made. Now, this of course being a function of the frequency ratio 2 zeta r over 1 minus r square, which means that for different speed values or excitation frequency value, we expect this phi to change, and that is what has been shown, that in the phase angle plot with different frequencies, depending upon the damping, the phase angle varied, right. It was close to 0, it was 90 degree at resonance, and it was approaching a value of 180 degrees at frequency ratio more than 1. So, let us have a look at this dynamic equilibrium for different values of forced frequency ratio. So, I am talking about or considering the case where the frequency ratio may be 0.55 or so, which means that it is operating below the critical speed or below the resonance. Okay. And that force polygon is what we have already discussed in the previous slide. So, it is going to be looking like that. Suppose this operation take place at a frequency beyond the resonance or beyond the critical speed, then you are operating more than 1 r equal to more than 1, and so somewhere there as 1.7 or 1.8 or so, and then if that is the case, the force will lag the response will lag the force by an angle phi, which is now going to be more than 90 degrees, and therefore, it is actually going to approach 180 degrees. So, the angle is obtuse here, the force vector will look like what you see in this green colored dashed arrow, and then the restoring force will still be aligned with x, the response, the damping force invariably it has to be at 90 degrees to the restoring force, given the way velocity and displacements are related for a harmonic response, and then of course, the inertia force m omega square x will create a force polygon like this, which is basically representing the dynamic equilibrium when you are operating post critical or post resonance and in a higher speed values. The last case, which is quite interesting, is when we are operating close to resonance. Okay. So, when we are operating close to resonance or at resonance, obviously, the force and the response, we have seen that at resonance the angle phi, we have talked about it a number of times, is pi by 2. So, which means that force and the restoring force and the response are going to be 90 degrees apart, and then your damping force and m omega square x are going to be creating almost like a rectangle. Okay. Now, there is one interesting thing that you must understand from this polygon is at resonance the restoring force and the force m omega square x they are equal and opposite, right. And how are the external force and the damping force? They are also equal and opposite. We have flipped these directions, but they mean the same. Okay. It is just because the way we wrote the equations of motion with force on the right hand side, but what it actually means that at resonance the external force is only countered by which force? The damping force. Okay. And therefore, that is precisely the reason why the damping plays most dominating and critical role at resonance or in the areas close to resonance, because that is the only thing that is counteracting. I mean, you can notice that this force partly it is being countered by the damping force and partly it is going to get countered by the difference between m omega square and kx. Whereas, at damping at resonance the only force that counters it by is the damping, dissipating force. So, a small amount of dissipating force is going to be very useful at the resonance. That is basically is your condition of resonance. Okay. Now, to further understand this phase is not so much talked about, but interestingly I will show you this phase how it is actually physically getting manifested is through a setup that we have in the lab. So, this is a simple vibratory system in the form of a beam which is hinged here. So, there is a fulcrum and this beam which you can notice here is the beam which is supported by a spring, okay, helical coil spring at its tip somewhere here. So, there is the restoring force due to this spring that is going to pull this spring this bar up when the bar tries to go down. All right. In addition to the beam, there is a huge mass here in the form of a motor. So, the beam has a motor situated somewhere here and that motor has a small gearbox which rotates two discs here. One you can very easily see here, this is the disc and similar another disc is on the other side. So, two discs are rotated by the operation of this electric motor through a small gearbox. So, the motor is having its axis here, but it splits into two at 90 degrees through the gearbox and then these discs rotate at some speed, and more important is that the disc has a small unbalanced weight which is attached here at this location. So, that the example of a forced unbalanced excitation is actually implemented here, which in addition you can notice a small dashpot which will be clear in the next picture, that dashpot is also there to give some amount of damping to this oscillatory system. Okay. So, these kind of setups are there in almost all our educational institutes, engineering institutes, and routinely we carry out a lot of experimental investigation on such small setups. So, again you have a hinge, this bar is nothing but your rigid bar all along up to this point and held by a spring at its end. This is representing the mass attached to the beam somewhere here. This is what dashpot that I meant. So, there is a viscous fluid in this and the piston and that creates a dissipating force. These are the two discs that I mentioned. These discs rotate about this axis and which essentially generates an excitation force in the vertical direction, and that causes this beam to oscillate as the discs rotate. Why? Because the force due to this unbalance is the excitation force F of t. This picture shows the unbalance that is bolted to the disc here. So, if I take this as an axis of rotation, the unbalanced excitation force will act like this. Okay. So, to show the schematic of this entire setup, it can be shown like that. It is the beam is hinged here and then it is oscillating about this hinge given an excitation. So, I can perturb it and give it initial gentle push and then it will keep on oscillating. But this motor with this particular excitation disc can be represented like a mass and unbalanced excitation like this. Okay. There is of course a dashpot here. So, you can see that there is a dashpot which is attached here schematically I can show like a dashpot like that, and then the mass sitting here and the restoring force created by the spring which is at the tip, like. So, this is the end of the beam where the spring is connected. So, you have this kind of a spring mass dashpot system comprising this particular vibratory system. Now, what we are going to do is we are going to show, if I start operating this motor with certain speed and operate this motor at a speed less than the critical and more than the critical, how does this relationship between the force and displacement plays out. So, this is the vibratory system that I thought let me first introduce to you, and then look at how this phase relationship actually is physically seen. So, what we are doing is we are operating somewhere here or so, I mean less than the resonance speed ratio omega equal to omega n, we are going to operate it lower than that, and we know that from the phase angle variation, when you operate it lower than the critical speed, the phase angle phi is less than pi by 2 or 90 degrees. Usually for a low level of damping, it is very close to 0 or it is maybe 10 degrees, 20 degrees or so. How does it show up here? So, let us look at that.
This is below critical speed.
So, you can see that you know the we have pasted a small reflective tape here, which is shown over here. That basically is aligned with the unbalance that is located. Okay. So, this unbalance actually is therefore going to indicate that there is the force is acting in this direction. Okay. So, as the disc rotate, the reflective tape here also rotates and basically shows the direction of the force acting on the disc and therefore on the entire beam. Whereas, you may see that you know look at this pencil which is connected to the end of the rod, or you can you can view this part which is basically going to show how the response of the system is going to look like. Now, our job is not to really bother about the amplitude or anything, but look at how you know this force and the response here. Maybe you can also look at this particular part depending upon which one is giving you a larger motion, so as to correlate the response and the force and their relative phase. Okay. Now, you can see that I am using this digital tachometer to ensure that I am operating really below the critical speed. Most important is to look at how the motion of the pencil and the force. So, you can see that as the force goes down, so you can see as this one is going down, the pencil goes down, this is going up, pencil goes up, and so on.
140 rpm.
In the second case, when I am operating here, which is post critical or post resonance. So, I will also play out this one slowly. So, you can maybe you can see as the unbalanced mass which is represented by this white strip, as the white strip goes down gradually, right, the pencil is going up. You can see that pencil is going up, the mass is going down, and the unbalanced force going up, the pencil is going down. Okay. Then as this is going down, the pencil is going up. So, you can correlate. The displacement is opposite in phase to the force. So, you can see this here, it is very clear. So, as the mass is going down, the pencil is up, and as it is going up the pencil is going down. So, this is how the phase relationship between the force and the displacement. It is getting played up, right. Is that clear to you now? So, this is what physically it happens, that the vibratory displacement of our vibratory system, when it happens under the harmonic excitation force, and if it is operating beyond critical where the phase between the force and the response goes beyond 90 degrees, as the force is going up and it's reaching its peak, the displacement is going on the other opposite direction. So, the vibratory motion goes down, but the force goes up, which is hard to realize, but then that is what is going to happen. Okay. Now, going ahead, the next important topic in the forced vibration response to harmonic excitation is a term called quality factor. Okay. So, we again start with the ratio that we have derived, x over x s t. That ratio is given by this expression. What is the maximum value of this response, capital X? So, if we see that if I plot this x over x s t, and please note that we all the time plot the modulus of this x over x s t. The reason is that it has a slightly different variation, but we all the time plot the positive values, because after you cross the resonance the amplitude capital X becomes negative. Okay. So, for example, x over x s t for an undamped case is going to be 1 over 1 minus r square, and therefore, if r becomes more than 1, then this entire ratio will become negative. Okay. So, actually the real way to plot this, or strictly speaking, if you plot this x over x s t, it is going to look like this, but we take the mod and plot, right, the absolute value, which means that the negative parts simply go flip like that, and then that is what you actually see here. All right. So, when you plot this particular the dynamic magnifier, you can notice that this peak is going to be actually will happen at frequency ratio of 1, which means that at the excitation frequency same as omega n. Now, what is omega n? This is undamped natural frequency, mind you. Undamped natural frequency means the natural frequency with damping ignored, but the moment we introduce damping, this peak shifts towards the left of this frequency ratio, okay, which means that the maximum amplitude is observed slightly on the left side of the resonance point, or the point at which the excitation frequency equals numerically to the undamped natural frequency of the system. Now, how do you find first how much is this peak value and at what speed you get that peak value? Okay. At that speed meaning at what excitation frequency value. How will you find that? Mathematically it is quite straightforward. What are you plotting here? You are plotting this value. Okay. So, if I want to know at what is the frequency at which I get this peak and what is the value of that peak, is I will take a derivative of this ratio with what? With r, which is varying quantity here. So, if I take ddr of this x over x s t and equate it to 0, because that slope has to be 0 at the peak value. Okay. So, if I equate this derivative taken with respect to frequency ratio r and equate it to 0 and solve that equation, I will get an expression for r. Okay. So, that part is of course left to you to figure it out. So, that derivative with respect to I mean is equal to 0, that will give you the ratio R, which is nothing but what, omega over omega n, and this is a specific R value. So, I will call this as R p and omega as omega p, because that is the frequency at which peak amplitude is going to be obtained for a given damping ratio, and it is found that this particular ratio is equal to 1 minus 2 zeta square. Okay. You can do this mathematical exercise and verify it yourself, that it turns out to be square root of 1 minus 2 zeta square. Okay. So, the magnitude is going to be by substituting this R p value in this expression. So, when you substitute in this very expression, which is valid for all values of R, if you replace this R with this expression and solve it, you will get a expression for x over x s t, and that would turn out to be 1 by 2 zeta. Okay. So, this is the frequency at which you get the peak value. So, omega p is equal to omega n square root of 1 minus 2 zeta square, and when you substitute omega p over omega n replace R with that ratio, you will get x over x s t equal to 1 by 2 zeta. It is a very simple straightforward exercise for you to get that relationship. The relationship tells us that x over x s t at R equal to R p is equal to 1 by 2 zeta, which means that given a particular damping value, the omega p is this, and if you use that omega p and the ratio with natural frequency, this is basically your R p, then at that R p value the amplitude here is given by 1 upon 2 zeta. Obviously, it has to depend on the damping ratio, which is clear from this graph that the peak amplitude is dependent on the damping ratio, and the quantification of that has come from this expression. Now, the maximum amplitude itself, as I showed here, is given by x p, which is x s t divided by 2 zeta. Now, we introduce now here a very important factor in forced vibration case, and that factor is called quality factor, which is defined as the ratio of the maximum amplitude to 0 frequency amplitude, and that ratio is indicative of how sharp the resonance is. Okay. So, this ratio Q as it is defined is the ratio of x p over x s t. Now, we have already shown the expression for x p is x s t over 2 zeta, use this to get x s t in the numerator here, and that is how I have written it here, divided by x s t. So, obviously, this basically is 1 upon 2 zeta. So, quality factor Q is given by the expression 1 over 2 zeta. So, smaller the damping ratio, sharper will be the response, because the denominator becomes smaller and smaller, and then it will create this ratio bigger for a very low level of damping. Just to give you an idea about this quality factor, if I take zeta equal to let us say 0.01, then obviously you have this as 1 upon 0.02, which gives you what value of 50. Quality factor is 50 for a damping ratio of 0.01. You might be aware the damping ratio, equivalent damping ratio, damping factor of the structural steel is roughly of the order of 0.0045, whatever it is in the third decimal place, right. It depends upon the real composition and all, but generally that is the range, it is less than 0.01. Okay. So, you can imagine that if there is no additional damping in a structural vibration case, the resonance can be very sharp. And what this 50 actually means to you, that the peak amplitude will be 50 times the amplitude of 0 frequency. Okay. This quality factor, if I use a zeta value of let us say 0.03 or 0.2, sorry 0.2, forget about this. So, if the damping ratio goes beyond 0.1, let us say 0.2, so then you have 0.4 here quality factor. How much will that be? 2.5. Okay. So, the moment damping factor goes beyond 0.1, you have much flatter resonance. So, the resonance in the first case could be like this, a very sharp one, whereas in the second case the resonance could be like this, a flatter resonance. Okay. Therefore, quality factor as one single number gives you an idea of how sharp the resonance is or how strong the resonance is. Okay. That is the beauty of or the relevance of quality factor. So, in practice people will talk about more commonly about quality factor of the vibratory system than the damping factor, okay, usually. So, quality factor then will give a quantitative estimate of the sharpness of the amplitude at resonance, no. So, or overall sharpness of the resonance condition. Now, we will have a look at how the damping is estimated in a practical vibratory system. Okay. So, now we are going to consider a similar kind of a practical vibratory system shown schematically like this, and you remember this, recall that this was a wind turbine case that we discussed, and then you have a harmonic excitation generated because of the rotation of the bladed end of the rotor with long turbine blades. These blades will inherently have some kind of an unbalance, and that unbalance will create an excitation force which is going to harmonically vary in a rotation, and that is how it is going to excite the system in a forced vibration way. Now, that is going to, so if I start rotating this shaft at different speeds, I know that as the speed increases the amplitude will keep on growing. As it nears the resonance or undamped natural frequency of the system, this will peak and then further fall and then go flat from there, right. So, suppose I practically measure the vibratory amplitude. Now, I can always show a vibratory equivalent vibratory system to be a simple spring mass system, okay, and this excitation force is going to act like this on the mass, and that is going to create a forced vibration response. Now, if I and this is basically what f naught e to the power j omega t, and if I keep on changing the frequency, I will get the amplitudes which is going to vary the way it is shown here in this diagram. Now, if I get this practically by actual doing measurement, I know what is the peak value of my response. So, maybe I will call this as xp. Now, most of our mechanical vibratory systems, as you see here, they are not going to have a dashpot hanging around here and there, right. They will have structural inherent material damping. Okay. So, damping in most mechanical systems are going to be less than 0.1. Okay. So, they will be almost like much lower level of damping, and so it is almost every time that we say that this omega p is very close to omega n, which means that the peak is observed close to the undamped natural frequency of the system. Now, if I somehow plot this, okay, and locate where the peak amplitude is located and the value of it, I can locate a position which is 1 upon square root of 2 times the peak amplitude and find out the bandwidth of the the frequency bandwidth here. So, I will basically be able to know how much is this difference in the two frequencies, at which these 2 points are obtained. Now, everything will get clear shortly. What basically I mean is, if I get the peak amplitude observed or measured, I can locate a point of response which is 1 over square root of 2 times the peak amplitude of vibratory response, and the frequencies omega 1 and omega 2, where this response curve intersects this horizontal line which is drawn at xp over square root of 2, and then once I get these two omega 1 and omega 2 values, I will define frequency bandwidth here as omega 2 minus omega 1. If I do that and get this ratio, what is this ratio? The frequency at which peak response is observed and this frequency bandwidth which is omega 2 minus omega 1, then this is actually related to quality factor, or it is related, or it can be shown that this expression or this ratio is same as quality factor. Okay. Now, you remember from the previous slide what was the expression for the quality factor? It was 1 over 2 zeta, right, clear. So, if I get this practical vibratory system to get excited by operating it at different speeds, somehow get this response curve plotted, with that I can get xp, with that I can get this delta omega here, the frequency bandwidth, okay. Then that ratio can give me a numeric value of the quality factor, and because quality factor is equal to 1 upon 2 zeta, what is the relevance of doing that? I can assess the damping in the system, that is what damping estimation is, right. What is the alternate way of finding out the damping in a practical vibratory system? You need to know what is the actual damping in your system and Cc, that is the damping factor. Now, the way, if I ask you to find out damping factor for your system, you will first figure out what is the quantification of this damping coefficient. Okay. You never know in your vibratory system like this, if there is no dashpot, where is that C coming from, right? What is the alternate other method than what we are discussing here of finding out the damping in the system? You remember? Suppose there is a beam here, made of steel. I want to know what is the damping factor of this steel beam as a vibratory system. Okay. Maybe the beam has a mass sitting at the tip. What I typically do, you remember the logarithmic decrement that we discussed. So, I perturb this beam. So, I basically give a gentle small tap or displace it and then release it. Once I displace and release it, it means that I am giving some initial excitation to the system. Then there would be a time displacement plot that I will get. Okay. This is the amplitude and this is time. This graph, you remember, we have discussed for an underdamped case, the amplitude logarithmically decreases, and we defined a parameter called logarithmic decrement. It was shown to be 2 pi zeta over square root of 1 minus zeta square. You remember that? How did you obtain that? You obtained by taking a natural log of x1 over x2, two consecutive response amplitude. So, if this is x1 and this is x2, these two amplitudes will give me this ratio from practically measuring the free vibration response of the system, right. So, by putting some kind of a sensor or accelerometer to measure the vibratory response of this system, once I get this response measured from the vibratory system using sensors, I can track the amplitude decay, and then from that amplitude decay I can get x1 and x2, which means I get this ratio quantified, and because it is same as the logarithmic decrement, which is theoretically shown to be a ratio like 2 pi zeta upon square root of 1 minus zeta square. Now, for a low level of damping, this ratio can be approximated as 2 pi zeta, okay, equal to this value. So, once this is quantified, I have zeta found out like 1 upon 2 pi ln x1 upon x2. So, this value is already known from the practical measurement. I can get the estimate of the damping factor in the system. This damping factor is an equivalent viscous damping factor, I mean damping factor corresponding to equivalent viscous damping coefficient C. Okay. So, it is C equivalent because the system as such does not have any dashpot, there is no viscous damping here. So, we are saying that the damping which is equivalent to a viscous damping is obtained like this. That was the first damping estimate from a practical measurement process. Now, you imagine if you want to use the same thing in a structure like a wind turbine, will you be able to push that wind turbine and let it vibrate like that? It is not possible, right. So, for bigger and more complex systems, that particular approach of finding out the damping ratio is not viable. Okay. So, but in lieu of that, what you can do in this case is to operate this turbine or this particular structure at different rotational speeds and then get this kind of a plot, and then if you get a plot properly and accurately measured, it is possible to get estimate of the damping again damping ratio using a concept of quality factor. So, it is going to be 1 upon 2 into q, where q it is possible to show that it is the ratio of the peak amplitude peak amplitude frequency over frequency bandwidth. That frequency bandwidth is something which we are going to discuss. So, is this clear? So, this is the second alternate method of finding out the damping or estimating the damping in a practical vibratory system. Advantage here is that you already you can run that vibratory system for different frequencies, and mostly because they are run by external controllable excitation source, you can actually run them at different speeds and get that response curve. Once you do that using this half power points frequencies, you can actually get the estimate of damping ratio in the vibratory system. So, this method is called as the half power point method, and I hope you know that power is directly related to square of the amplitude, is not it? So, you all know that. So, if we have a half power, then what should be the amplitude be? 1 upon square root of 2 times, right. So, that the power related to the amplitude, which is 1 by square root of 2 of the peak amplitude, then you get power equal to half of the peak power. So, this is basically what we have is the basic philosophy behind locating the half power points. So, what we do is we plot this kind of a response versus frequency, okay, a plot as we have seen in the previous slide, that I can keep on changing the excitation frequency and keep on noting down the amplitude at each of those frequencies and somehow generate this graph, generate this response variation. Now, obviously, I know that this peak amplitude is defined or is referred to as xp, the peak amplitude, and similarly the frequency at which this happens is the omega p, that is the peak frequency or the frequency at which peak is noted. Similarly, half power points mean the amplitude xp should drop to a level which is 1 by square root of 2 times the peak amplitude, is not it. So, this point which I locate would be by by locating the amplitude which is 1 by square root of 2 times the xp value. Now, this is called as the this particular point is xp over square root of 2 and that value or that point is called as xh, the half power point. Now, once I locate this on the amplitude scale, I draw a horizontal line and locate these two frequencies. Okay. These two frequencies are basically going to give me frequency bandwidth delta omega. So, maybe I will call this as omega 1 and this frequency as omega 2. These are the two frequencies at which the amplitude drops by 1 by square root of 2 times the peak amplitude. Okay. Having said this one, what is xp over xst? You remember from the previous slide, the peak response amplitude is equal to 1 by 2 zeta. That is how we discussed and we derived that, right. So, omega p was shown to be omega n square root of 1 minus 2 zeta square, and if I substitute this frequency ratio omega p by omega n in the original expression, I get this ratio xp over xst equal to 1 by 2 zeta. That is basically the value that we already know. Now, if I take the half power point xh, then xh is xp over square root of 2, which means that xh upon xst is going to be xp over xst square root of 2. So, basically you divide this by xst and also to this by xst, that is basically the ratio that you get, and which actually means that it is because xp upon xst is 1 by 2 zeta, this is what the ratio that I have. Now, except this particular point, all these points on the response curve, they basically follow the same expression, this expression that we have got 1 minus r square whole square plus 2 zeta r whole square. This expression is valid for all these points. So, it will be valid for this point also. Okay. So, if it is valid for this point also and that point is actually the half power point, then I can write this half power point as this expression 1 upon this expression is nothing but this one, and I equate it to this particular right hand side expression, okay, because then this is going to be RH, which what is RH? RH is going to be the frequency either omega 1 by omega n or it could be omega 2 by omega n. Both of these two ratios should give me this equation fulfilled. Now, the job is to find out the expression for r's, this r square by equating the two. Why? Because this ratio which is xh upon xst is both given by this expression and it is also given by this expression going by our definition of the half power point. So, what we do now, what we do now is that we equate these two quantities, and if I equate these two quantities and reorganize it, please try it yourself, you will get a quadratic in r square. Obviously, you square both sides and then equate the denominator, that is what you are going to get, right. This is quadratic in r square. If you solve it, you will get two possible roots, one is r1 square given by this and the other one is r2 square. Now, just use your simple straightforward method of finding out the roots of this quadratic. So, there are two possible roots, one with this negative sign and the other one will be with the positive sign. So, there are these two expressions that you will get when you solve this equation. Now, here we make a small assumption. Okay. The assumption is we will ignore higher powers of zeta. Okay. Now, should there be a justification of ignoring this? Can you find out square root of 1 plus 0.01 square? And if I, with my assumption, what I am going to do is I will assume this to be equal to 1. You will find that this zeta square, as long as it is small enough, will make absolutely no difference numerically. Okay. Same thing happens here, 1 minus 2 zeta square. So, if the zeta is, even if the zeta is 0.1, let me tell you, even if zeta is 0.1, even then it will not make any difference numerically. Okay. So, it is perfectly valid for me to assume that this R1 square is approximately equal to 1 minus 2 zeta from the first expression. So, I am basically writing here as R1 square, this expression which I have got here. Okay. This expression which I have is written as this, and from the second expression R2 square I am writing as 1 plus 2 zeta. Okay. This is ignored or assumed negligibly small. Similarly, this bracketed term is assumed equal to 1. Okay. By ignoring higher powers of zeta, these are the simpler relationship. Of course, mathematically you may say that is approximate ones, but then you will find that numerically it really makes no difference unless your zeta is more than 0.3 or so, which is relatively rare in the mechanical vibratory systems. Okay. Now, what we do is that I will write this as R2 square minus R1 square. What is going to be that? R2 square minus R1 square will be what? 4 zeta. And what is R2 square minus R1 square, by the way? This is omega 2 square upon omega n square, because we have defined R2 and R1 as what? Frequency ratios corresponding to half power points. Please make a note here. This is what? This is your omega 1 and this is omega 2. We define R1 and R2 as the two forced frequency ratios corresponding to the, sorry, this is omega n, not omega 2, okay, minus omega 1 square upon omega n square equal to 4 zeta. Now, what I do? I can write this expression as omega 2 square minus omega 1 square equal to 4 zeta omega n square, and I write this as omega 2 minus omega 1, and then I write here what? Omega 1 plus omega 2. I can write omega 2 plus omega 1 equal to 4 zeta omega n square. Now, as per my definition, what is this delta omega? Omega 2 minus omega 1. So, this is my delta omega, and omega 2, this is another assumption that I am making here, omega 2 plus omega 1 upon 2, can I say that this is again close to omega n, or I can write that it is close to omega p, okay, because even if in some cases this may not be exactly symmetric, I can approximate it that the omega p will be algebraic mean of the two frequencies, half power frequencies. So, that basically will mean that I replace omega 1 plus omega 2 by 2 omega n, and I will retain omega n here and get rid of this 4 by dividing it by 2. So, omega 1 plus omega 2 by 2 is like omega n 2 omega n, and that 2 maybe I will write it here and then keep this necessarily confusion here 4 zeta omega n square. Now, what I have? Delta omega, okay, by 2 omega n is equal to zeta, which I can always write this as delta omega by omega n, and make a note here that this omega n is also for low level of damping can be like omega p. So, therefore, this delta omega over omega n, I may with slight the assumption that I mentioned, I write this as equal to 2 zeta. Okay. So, maybe so the other way to write this is that the same expression I can write as omega p by delta omega is 1 over 2 zeta, which itself has been defined by us as quality factor. Isn't that correct? So, peak frequency over frequency half power frequency bandwidth is directly related to the quality factor, which itself is directly related to the damping ratio of the system, and therefore, by measuring the vibratory response to forced excitation, harmonic force excitation, I can definitely get an estimate of damping without knowing the parameters of my vibratory system. Did I ever use any K or C or M here? No, right. The only catch here is this entire derivation is done based on what? X over XST expression, which is valid for constant frequency excitation, which means that constant amplitude excitation, that means F naught is not allowed to change with frequency of excitation. Whereas, the example that we started with wind turbine is a case of a forced vibration or force excitation due to unbalance, which changes its F naught value, the magnitude value. F naught is what? It is m e omega square, which means that it is the F naught itself is dependent on omega, okay. But it is left to you as an exercise to show that even with that expression, which we are going to deal with shortly, in the forced vibration case using unbalanced excitation also, this expression is still valid. That means, even if the excitation is through harmonic unbalanced excitation, you will be this expression of getting damping estimate from half power point bandwidth frequency bandwidth is also valid. Okay. So, the same method of finding out the damping using excitation through unbalanced excitation in a vibratory system is also valid. So, that is what you have here as another alternate method of getting the damping estimate. That is what measurement of this peak frequency, which you can always get by measurement, and delta omega by getting this half power point bandwidth frequency bandwidth, you estimate the damping straight away from measured data. You do not need to figure out what the mass is, what the stiffness is, what the damping is. Okay. What is going to be a challenge in using this method of estimation of damping? Suppose if I have a vehicle chassis which is being tested for its overall structural damping. People do testing on the chassis, body in white test, they call it, and then they put it. Now, there you do not have any excitation mechanism. So, the typical way in which such systems are excited are using large electrodynamic or many times hydraulic or pneumatic shakers. Okay. Those shakers are used to give excitation f e to the power j omega t, and then they measure the response. Okay. So, getting this curve itself can be challenging in some practical cases. Take the example of a railway coach, you are trying to do some estimate there. Okay. So, large systems are not so easy to excite, okay. And then you need all kinds of instrumentation here. The shakers are extremely costly. It's not so easy to have large size shakers everywhere. No? They cost a lot. So, testing that way is a big problem, but you imagine how simply you excited your simple vibratory system into into a free vibration decaying sinusoid response, you could simply put an accelerometer here and generated that response, but then it applies to simpler and smaller systems well. Okay. Many times you need to excite it, so people use impact hammer or small gentle tapis put. So, you can't do that with bigger systems. Okay. So, there are a lot of pros and cons in which these two alternate methods, one using logarithmic decrement and one using the half power point method, they do have their own pros and cons, and in different contexts different either of these two methods can be quite useful, but this is much more classical and more widely used because it applies to both small and big systems, but the challenge here is the cost of doing those. So, estimates. So, that's the way, but then this is the way in which you can get an equivalent viscous damping estimated of your system. So, that damping could be contributed by variety of sources. It could be material damping, it could be interface friction somewhere if you are if you have multiple interconnected parts, and if they are bolted ones, then there will be slipping that is going to happen, there will be friction damping somewhere. So, all of them will contribute to a unified equivalent damping estimate. So, you that way then you do not have to bother about whether it is a material damping, whether there is some other kind of a damping taking place there, and so it is that way a very nice way of getting an estimate of the damping in a practical vibratory system. So, that is the advantage here. So, the summary of this lecture, we had a detailed discussion on the phase relationship between the forcing function and the response, and also reviewed how the governing equation of motion is in fact a dynamic equilibrium, a force equilibrium case, and the phase between all the components of the forces acting on a vibrating body are related. Frequency at which the peak response is obtained, we also got an equation for that frequency, and then a concept of quality factor has been introduced. The significance, practical significance of knowing a quality factor for a given vibratory system has been highlighted. The questions based on this discussion, these are the two questions which you can attempt, simple and straightforward as such, but we will test whether you understood the concepts. These are the answers.